Right, we're going to start off Unit 2, which is mostly about atomic structure. We're going to begin, though, talking about how to classify matter, because when we can classify something, a lot of times we understand it and are able to organize it in our heads a little bit better. So the first thing we have to do is talk about what chemistry is. So far, we've mostly just done measurement and unit conversions and things like that. Chemistry is the study of matter and how it changes. So reactions, physical changes, those are all things that we're going to be talking about. And matter is defined as anything that has mass and takes up space. So mass and volume. Okay. If you're curious, mass and weight are somewhat similar. Mass is just like the amount of stuff in something, and it never changes regardless of gravity. Whereas weight is taking into account the force of gravity on an object. So you would weigh different on the moon, even though you contain the same amount of mass because there's less gravity on the moon. So things that are not matter, that don't have mass and take up space, time, gravity, visible light, UV, things like that, energy. In terms of if you have a chunk of matter and you want to break it down into categories, you can better understand it. You can first categorize anything as either a pure substance. So some examples would be water, gold, table salt. So those are things that are pure. They can't be easily broken down. And then mixtures are a little bit easier to break down. Soup would be an example, so like vegetable soup. Paint, even though it maybe doesn't look like a mixture, if you let it sit long enough, you'll see it separate into, maybe the pigments and things like that at the bottom and the water at the top. If it's water-based paint. Brass, again, looks like a pure substance, but it's actually a mixture of a couple of different metal elements. All right, so if we wanted to separate a mixture, we can actually do that by physical means, meaning that it doesn't require a chemical reaction. So, for example, if we're talking about separating a a saltwater mixture, we could take advantage of the fact that water boils at a much, much lower temperature than salt does. So if you have a mixture of salt and water, you can simply boil away the water, leave behind the salt. So to understand what this looks like and what's actually happening here, if I have a pot or a beaker of water, right? So, and then I go ahead and dissolve some salt in it. So those salt particles, they're actually called ions. We're just going to keep it simple and say that the salt is very dissolved, it's well mixed. So this would be a homogeneous mixture. The salt particles would actually be so small. I know I'm drawing them so you can see them, but they would actually be so small that you couldn't even see them. And then, of course, you apply a little heat. Put this on a Bunsen burner flame or a hot plate or something. And then a little bit later, now maybe you walk away for a little bit. That wouldn't be too safe. But if you did and you came back a little bit later, you would notice that those salt crystals would have gathered up together at the bottom of the beaker. Maybe some of them stuck to the sides of the beaker. And the water, of course, has all gone. The water still exists. We didn't destroy it, but now it just exists as these little gas particles floating around in the air. So we just separated a salt-water mixture through physical means. In this case, the physical means would just be boiling. Okay, a pure substance, on the other hand, can only be separated by a chemical reaction. So, for example, if I had a sample of water, so some water molecules, a lot of times will show the oxygen it is actually quite a bit larger than the hydrogen. So a water molecule is just made up of two hydrogens and an oxygen. So it would look kind of like this. All right. So I got two water molecules. Now, if the sample of water were to simply boil, all that means is they just sort of head off in opposite directions. it doesn't actually change the water molecules themselves because that's just a physical process. So since water is a pure substance, H2O, it has a formula, it is a compound, okay? And we'll talk about compounds in just a minute, but it's a pure substance. So in order to separate it, you would actually need to have a chemical reaction. So you do a chemical reaction to this thing, and now all of a sudden the oxygens and the hydrogens separate from each other. And in this case, the oxygens would reattach to each other, and the hydrogens would also reattach to each other. And I meant to show my hydrogens originally as these little green guys, but you get the idea. They're the same as these little guys over here, okay? So we've done a chemical reaction, and what we ended up with in the end is something very different. We have some H2 molecules, and we have some O2, or excuse me, one O2 molecule. So we created something different, something new, something with different properties. So that would be the only way to separate a pure substance. Okay, so pure substances have what we call constant intrinsic properties, and those intrinsic properties can be used to identify them. And so what do we mean by intrinsic? Intrinsic just means internal and unchanging. So all substances have whether it's melting point, boiling point, hardness, density, color, they have properties that don't change just because you chop the sample in half, or just because you melted it and refroze it, or did something like that physical to it. When you see an Olympian winning a gold medal and then biting the medal on the medal stand, well, that's a tradition, but it comes from the intrinsic property that pure gold, right, if it's not mixed with anything else, it's 24 karat gold, is very soft for a metal. And so we're taking advantage of, the tradition comes from, long ago when people would exchange gold coins for, for products and services and things like that. You wanted to make sure that it was actually gold that you were getting, and so if you bit it and your tooth sunk into it a bit, you knew that it was probably pure gold, or at least pretty close to pure gold. So hardness, like the relatively low hardness of gold, is an example of one of its intrinsic properties. Boiling point, solubility in water, so does it dissolve in water? Is it very dense? Its color, these are all things that can be used to identify not just gold, but any pure substance. So if you think about water, water has a boiling point of 100 degrees Celsius. If it's not pure water, that's, if you sprinkle in some salt, that actually changes its boiling point, because now you have a mixture. It's no longer pure water. Or if it's a different liquid like ethanol, it's going to boil at a lower temperature because it has that different intrinsic physical property. Some examples of properties that are not intrinsic, we call these extrinsic: mass, volume, shape. So water doesn't change its boiling point because you poured a larger glass of it, but it does change its mass, its volume, and potentially even its shape if you pour it into a different container. So those are not identifiable characteristics or properties. Okay, so pure substances. We've already talked about everything can either be a pure substance or a mixture. Pure substances can be even further subdivided into elements and compounds. Elements are, of course, just one kind of atom from the periodic table. So we have periodic tables that we'll get for this class. We have them hanging on the wall, but basically just the 118 or so known elements are considered their first type of pure substance. So example, gold, hydrogen, helium, carbon, oxygen. Notice a couple of these even have subscripts like H2 and O2, and that simply means that they're paired together, they're chemically bonded together, but because there's only one element in that substance, like there's only oxygen in O2, we still call it an element. Compounds, on the other hand, will always have a formula because they're made up of two or more elements chemically bonded. So H2O, CO2, etc. And again, these can be separated, but not through boiling or filtering or decanting or anything like that. They can only be separated through a chemical reaction. Mixtures can also be subdivided. They can be heterogeneous, which simply means it's easy to tell that this thing is a mixture. For example, we've got a picture again of our vegetable soup. You can see the different pieces. Tomato soup might be a little harder to tell, right? Because it looks the same throughout. Concrete that's got the pebbles mixed in with it, aggregate concrete would be an example of heterogeneous. It just means different. It means it's not the same throughout. These are easy to tell that they're mixtures. And then homogeneous mixtures are just well mixed. They look the same throughout. So it looks like a pure substance. So, Coca-Cola would be an example of a pure substance because, sorry, it would be an example of a homogeneous mixture, not a pure substance, because it looks kind of like it could be a pure substance. If it weren't in a Coca-Cola bottle, you may not know what it is, and you may think, oh, this is, some chemical that we have a formula for that's only made up of 2 or 3 elements chemically bonded together. Well, we know because, we've seen the ingredient list that there's actually tons and tons of different pure substances that make up that Coca-Cola. So those are our categories. We've got mixtures and pure substances. Among pure substances, we've got elements and we've got compounds. And then among mixtures, we have heterogeneous and homogeneous. And we're going to continue to work in the lab to talk about how we can separate some of these mixtures into their pure substances.